To recap the video we watched at the end of the last session, here is a brief summary of how hashed password works. So to load a new password into the system, the user selects a password. The system then combines the password with the fixed length salt value. The password and the salt value serve as inputs to the hashing algorithm to produce a fixed length hash code. The hash algorithm is designed to be slow to execute in order to prevent attacks. The hashed password is then stored together with the plaintext copy of the salt value in the password file for the corresponding user ID. When the user attempts to log into the system, the user provides the ID and the password. The operating system uses the ID to index into the password file and retrieve the plaintext salt value and the hashed password. The salt value and the user-supplied password are then used as input to the hash algorithm. If the result matches the stored value, then the password is accepted. One way to impede a password attack is to deny the attacker's access to the password file. If the hashed password is accessible only to the privileged user, then the attacker cannot read it without already knowing the password of the privileged user. Often the hashed passwords are kept in a separate file from the user IDs. This file is referred to as the shadow password file, to protect the shadow password file from unauthorized access. Although password file protection is certainly worthwhile, there remain vulnerabilities. Many systems are susceptible to unexpected break-ins. A hacker may be able to exploit a software vulnerability in the operating system to bypass the access control system to extract the password file. Alternatively, the hacker may find a weakness in the file system or database management system and allow access to the file. A list here on this slide provides some vulnerabilities that are associated with the password-based authentication. To mitigate these vulnerabilities, a password protection policy must complement access control measures with techniques to force users to select passwords that are difficult to guess. The National Institute of Standard and Technology's special publication recommends several requirements in terms of regulating password selection for both credential service providers and verifiers. System-selected passwords are often provided by the credential service providers at enrollment or by the verifier. Some guidelines are available for system-selected passwords. These guidelines are provided in your textbook. Next, we're going to move on to position-based authentication. Objects that are often used for the purpose of user authentication are referred to as hardware tokens. Several types of hardware tokens are widely used, and they're listed here on this slide. The first example of hardware token we're going to introduce is memory cards. Memory cards store data but do not process data, and the most common example of such cards are bank card or gift card, with a magnetic stripe on the back, which stores only a simple security code and can be read by an inexpensive card reader. Memory cards can be used alone for physical access, such as a hotel room. For authentication, a user provides both the memory card and some form of password or personal identification number. However, several potential drawbacks exist. First, memory cards require a special reader, which increases the cost and additional security requirements for the reader hardware and software. Second drawback is the loss of hardware token. A lost hardware token temporarily prevents its owner from gaining access to system resources. The third drawback is user dissatisfaction. The use of a memory card may be considered as inconvenient by the users. The second physical token we're going to introduce is smart tokens. A wide variety of devices are qualified as smart tokens. They are often categorized based on 4 dimensions, including physical characteristics, user interface, electronic interface, and authentication protocol. For user authentication, the most important category of smart token is smart card. Smart card has the appearance of a credit card and also contains an entire microprocessor, including memory, processor, and input and output ports, which allow the card to communicate with the card reader. Smart cards are increasingly used as national ID cards for citizens. The other type of physical token we're going to introduce here is the devices that generate one-time passwords. The use of one-time password improves security by preventing the risk of guessing and reusing a password, especially if used together with other authentication mechanisms. The most widely used one-time password device provides a user with a physical card or other hardware token that displays a new pseudo-random number at frequent intervals, usually 1 minute. The device has an embedded secret that is used as a seed for the generation of one-time passwords. To authenticate, the user types both the currently displayed pseudo-random number and a personal identification number that the user must remember. Therefore, it is a two-factor authentication. Hardware tokens are vulnerable to a variety of threats such as theft, duplication, eavesdropping, replay, denial of service, and host attack. A number of security controls can enhance the security of hardware tokens, and they are listed here on this slide. The last authentication factor we're going to introduce here is the biometric authentication. A biometric authentication attempts to authenticate an individual based on the physical characteristics, including static characteristics such as fingerprints or facial characteristics, or dynamic characteristics such as voice or handwriting. The list here on this slide shows the common physical characteristics used in biometric applications, and the graph provided here is a rough indication of the relative cost and accuracy of these biometric measures. The operation of a biometric system is illustrated in the following figures. Each individual must first be enrolled in the system. This is analogous to assigning a password to the user. For a biometric system, the user presents a name and typically some sort of password or personal identification number to the system. At the same time, the system senses some biometric characteristics of the user, such as fingerprints of the right index finger. Then the system digitalizes the input and extracts a set of features that are stored either as number or a set of numbers, representing the unique biometric characteristic. This process enrolls the user into the system. User authentication on the biometric system involves either verification or identification. For verification, the user enters the personal identification number and also uses a biometric sensor. The system then extracts the corresponding feature and compares that to the template stored for this user. If this is a match, the system authenticates this user. For identification, the user uses the biometric sensor but presents no additional information. The system then compares the presented template with the set of stored templates. If there is a match, then the user is identified. In any biometric scheme, some physical characteristic of the individual is mapped into a digital form of representation. For each individual, a representation or template is stored in the computer. When the user is to be authenticated, the system compares the stored template to the presented template. Given the complexity of physical characteristics, it often does not expect to be an exact match between the two templates. Rather, the system uses an algorithm to generate a matching score that quantifies the similarity between the input and the stored template. Two concepts are typically used to evaluate the accuracy of biometric system. First is the false match rate, which refers to the frequency that the biometric samples from different sources are erroneously assessed to be from the same source. Second is the false non-match rate, which refers to the frequency that samples from the same source are erroneously assessed to be from different sources. For a given biometric scheme, this figure on the slide plots the false match rate and the false non-match rate to obtain the operating characteristic curve. The figure shows idealized curves for two different systems. The curve that is lower to the left performs better. The dot on the curve corresponds to a specific threshold for the biometric testing. Shifting the threshold along the curve up and to the left provides greater security and the cost of decreased convenience. There are 11 known attack service points in the biometric authentication system where an attacker could potentially interject into the flow and interfere with the authentication decision. These 11 elements may be all self-contained within a single device, such as the mobile device, or distributed across multiple physical systems. The most important security control for biometric authentication is presentation attack detection. The presentation attack detection involves two types of methods to directly counter spoof attempts at the biometric sensor. Artificial detection attempts to answer whether the biometric sample at the sensor is artificial. The other type of attack detection is liveness detection, which attempts to answer whether the biometric sample at the sensor is from a living human presenting a sample to be captured. The goal for presentation attack detection testing is to test a set of materials that present a potential attack level and also determine the maximum error rate found among these materials. The National Institute of Standards and Technology supports only the limited use of biometrics for authentication. For the last part of this lecture, we're going to introduce access control. Access control refers to the process of granting or denying specific requests for obtaining or using information and related information processing services. Subject, object, and access right are the basic elements of access control. A subject is an entity that is capable of accessing object and is typically held accountable for the actions that he or she has initiated. An object is a resource to which access is controlled. In general, an object is an entity used to contain or to receive information. Finally, an access right describes the way in which a subject may access an object, such as read, write, delete, create, search, and execute. An access control policy dictates what kind of access are permitted, under what circumstances, and by whom. Access control policies are generally grouped into 4 categories, including discretionary access control, mandatory access control, and role-based access control. Discretionary access control is an access control that is based on the identity of the requester. It is also based on the access rule that stating what requesters are allowed to do. The controls are discretionary in the sense that a subject with certain access permission is capable to passing that permission on to any other subject. A general approach to the discretionary access control is to use an access matrix. One dimension of the matrix consists of identified subjects that may attempt to access the resources, whereas the other dimension lists the objects that can be accessed. Therefore, each entry of the matrix indicates the access rights of a particular subject for a particular object. In practice, an access matrix is usually sparse and is implemented by decomposition in one of 2 ways. The matrix can be decomposed by columns, creating access control lists. For each object, access control lists the users and their permitted access rights. When it is desired to determine what access rights subjects have to a particular resource, access control lists is convenient because it provides the information for a given resource. However, this data structure is not convenient for determining the access right available for a specific user. Decomposition by roles creates capability tickets. A capability ticket specifies authorized object and operations for a particular user. Each user has a number of tickets and can be authorized to loan or give them to others. Because tickets can be dispersed around the system, they present a greater security problem than access control lists. Therefore, the integrity of ticket must be protected and guaranteed. Mandatory access control refers to an access control that is based on comparing security labels with the security clearances. Security labels indicate how sensitive or critical system resources are with security clearances. Security clearances indicate whether system entities are eligible to access certain resources. This policy is termed mandatory because an entity that has clearance to access the resource may not enable another entity to access that resource. The role-based access control is an access control that is based on users' roles. The role permissions can be inherited through a role hierarchy and typically reflect the permissions needed to perform defined functions within an organization. The role-based access control is based on the roles that the users assume in a system rather than on the user's identity. Typically, it defines a role as a job function within an organization. The role-based access control system assigns access rights to role instead of individual users. Therefore, according to their responsibilities, users are assigned to different roles. The tables here on this slide represent the access control matrix. The left matrix relates individual users to roles. Each matrix entry is either blanked or marked. Marked indicates that this user is assigned to this role. The right matrix, as the discretionary access control matrix, has the same structure with roles and subjects. Typically, there are few roles and many objects or resources. The entities within the matrix represent the specific access rights permitted to the roles. Attribute-based access control indicates an access control that is based on attributes. Attributes are characteristics that define specific aspects of the subject, object, environment conditions, or requested operations that are predefined and pre-assigned by an authority. There are three types of attributes in the attribute-based access control model. The first one is the subject attributes. It refers to the characteristics of the subject, such as the subject's identifier, name, organization, job title, or subject's role. The second is the object attributes. It is about the characteristics of a resource, such as the device name or a location. The last is the environment attributes. It describes the operational, technical, or even situational environment or context, such as the current date and time, the current hacker activities, and the network security level. Attribute-based access control is a logical access control model that is distinguishable because it controls access to objects by evaluating rules against the attributes of entities, operations, and the environment relevant to the request. Particularly, it relies on the evaluation of attributes of the subject, attributes of the object, and a formal relationship or access control rule. The figure here on this slide shows the essential components of an attribute-based access control system.